So the overall strategy is very similar to what we did in chapter 1. You do want to start by considering the associated homogeneous equation. The associated homogeneous equation where the forcing function is 0. There is no external forcing. The only forces acting are Hooke's law and friction, damping. I'll just write it with prime notations to save time. Y double prime plus 7y prime plus 12y equals 0. We've done that kind of equation a lot recently. You don't have to convert to a system. You can just come up with a scalar equation. If you guess y equals e to the st, by differentiating and so forth, this leads to an equation involving s that's quadratic, s squared plus 7s plus 12 equals 0. You can always use the quadratic formula, but in this case, I did make it relatively easy to factor. The roots are -3 and -4. The order they're in doesn't matter. And all this then gives you a general solution of the corresponding homogeneous equation, which we'll call YH, to be an arbitrary linear combination of e to the -3t and e to the -4t. Say k1 e to the -3t plus k2 e to the -4t. Some linear algebra that can be commented about here. You could think of this left-hand side of this homogeneous equation, or the original equation for that matter, because they're the same, as being a second-order linear differential operator, which is really a linear transformation between function spaces. Bringing to mind some linear algebra that you should know for exam 4, that kind of idea. What function spaces? Well, it's kind of somewhat of an arbitrary choice, but the choice I usually make is the domain of T being C2R, meaning twice continuously differentiable functions on the entire real number line. They have first and second derivatives that are all continuous everywhere. 2CR, the vector space of all just plain continuous functions on the real line. Why does it have to go from C2 to C? Because we're differentiating. We could lose the ability to take another derivative, for example, if we're only assuming twice differentiable, not assuming 3 times continuously differentiable. Our outputs for this linear transformation are in general not necessarily differentiable, but they will be continuous. The solution space of this homogeneous equation is the kernel of this linear transformation. I'm looking for all functions that get mapped to the 0 function. Kernel of linear transformation is a subspace of the domain. It'd be a subspace of this, but it is a finite dimensional subspace. This vector space is infinite dimensional. There's no finite basis for it. There's plenty of functions in there that don't even have names. But its kernel is finite dimensional, and it turns out through some theory that I never get the time to actually write down in the lectures, second order linear equations like this have solution spaces that are 2-dimensional vector spaces. So once you've got 2 linearly independent solutions like this, an arbitrary linear combination of them will span the solution space and therefore be a general solution of this homogeneous equation. But now we want to go back to the original non-homogeneous equation. That was what we're really after. So we need our second step. Find a particular solution of the original non-homogeneous equation, forced equation. Let me go ahead and use the word forced. That's forced there, forced equation. Forced is synonymous with non-homogeneous. There's an external forcing function. It is, in many models, a force. And therefore, that's why we call it a forced equation. Does it have to be a force? No, I suppose there could be some application where it's not a force. But in most applications, it is some external force because in most applications, this is a harmonic oscillator. Call it YP. And what should YP be? What did you guess? Anybody who did guess? Go ahead, Greg.
Something like some constant times e to the negative 2t.
Yeah, some constant, maybe call it capital A times e to the negative 2t. Why? Because it's a logical guess. I'm looking for a function whose second derivative plus 7 times itself plus 12 times itself. Second derivative plus 7 times its first derivative plus 12 times itself always equals e to the negative 2t, no matter what t is. Something times e to the negative 2t is a good guess. Differentiate that twice with the chain rule. Plug it into the original non-homogeneous equation on the left side, set it equal to the right side, see if you can solve for capital A. It's possible you won't be able to solve for capital A. It's possible this is a bad guess in theory, but in practice, I know it's a good guess. It will work. So I'm plugging it into the left-hand side of the original differential equations. There it is. Plug it in. Be careful not to make a mistake. There's the second derivative. 7 times the first derivative is going to be minus 14a e to the negative 2t. And then 12 times the function is going to be plus 12a e to the negative 2t. Simplify, collect those like terms. Looks like it's going to be 2a e to the negative 2t. 4 minus 14 plus 12 is positive 2. I'm setting this equal to the original right-hand side, which was just a plain e to the negative 2t. Those will be equal if capital A is 1/2. Two A equals 1/2, so A is 2a equals 1, so A is 1/2. Therefore, YP is 1/2 e to the negative 2t. Last step is to write down your general solution of the original forced equation. The associated homogeneous equation is unforced equation. No external forcing. The original non-homogeneous equation is forced. The general solution of the original non-homogeneous equation, forced equation, just like in chapter 1, is YH plus YP. So in this case, that becomes K1 e to the negative 3t plus K2 e to the negative 4t plus what we just found for YP, 1/2 e to the negative 2t. And then you can use this to solve initial value problems. You need not only an initial position, y of 0 equals something, but also an initial velocity, y prime of 0 equals something. And that would help you solve for the two unknown constants, K1 and K2, to get a unique solution of an initial value problem. So this is not too much different than what you did in chapter 1. We're just upping the first order equation to being a second order equation. But the overall big picture ideas are the same. You can convert this to a system. What would it be if you did? And you should be able to. It would be dy dt equals v. That's always the same first equation. Definition of the velocity. And then dv dt would be, careful here, negative 12y minus 7v, bringing those over to the other side. Don't forget the forcing part, plus e to the negative 2t. And that is a non-autonomous system because it involves a t on the right hand side. If I were to draw the vector field, it would not be a static vector field. It would be changing over time. The dv dt, second component of all the vectors in the vector field, would be changing over time, in fact, getting smaller over time, because this goes to 0. It goes to 0 fast enough that after a short amount of time, it wouldn't look like it's changing anymore. It would look static. But you would see a slight change in the vectors at first. I won't take the time to make it in Mathematica. It would be non-autonomous. Because it's non-autonomous, solution curves actually can cross. Do you remember that in the lectures about non-autonomous systems? And that does not violate uniqueness. Intuitively, it's because the vectors in the vector field are changing. So distinct solution curves actually can touch each other. And that does not violate uniqueness. Okay. Things to keep in mind as you consider more examples in homework and do the reading as well. Can I clarify anything? It does, this is section 4.1 type of problem. It does get harder in section 4.2 as you would expect when we have cosines and sines for the forcing, which are more realistic. And I always make it analogous to think of the mass as being on a table going back and forth, and the external forcing being you grabbing the table and moving it up and down, shaking it like that, side to side, as being an analog of how the external force could be a cosine or sine. And I will say things get tougher. How do they get tougher? Well, they get tougher especially in trying to find yp, because, well, there's two ways to approach it. You either guess some combination of cosines and sines here with two unspecified constants, or we go back to using complex numbers again, it turns out. And that is the approach we take. We go back to using complex numbers, and there's a lot of benefits to that. Okay, so complex numbers are coming back again soon. All right, I'd also like to look at a diagonalization example today that I think probably would be best to do on Mathematica, though you may want to write some things down. Let's take our coefficient matrix A for, well, this could be a system of differential equations. It could be a system of difference equations. Could be either way. Let's make it be this kind of symmetric looking matrix. And in fact, that matrix is special enough that we actually do call it a symmetric matrix. It does have symmetry. The symmetry really refers to these two numbers being the same, the 3's, not the 2's. Yes, I did make those numbers in the main diagonal the same because it makes the calculations work out nicer. However, even if those numbers were different, I would still call it a symmetric matrix. For a 2x2 case, what makes a matrix symmetric is if these numbers in the off diagonal, upper right and lower left, if those numbers are the same. Technically speaking, in general, including for 3x3 and 4x4 and 5x5 matrices, etc., a symmetric matrix has the property that it equals its own transpose. This is the definition of a matrix A being symmetric in the 2x2 case for an arbitrary 2x2 matrix whose entries are A, B, C, D. If I take its transpose, remember you flip the rows and the columns. The first row of the original matrix becomes the first column of the transpose. And the second row of the original matrix becomes the second column of the transpose. Those two things are going to be equal. Well, okay, that's good. That's going to equal A, excuse me, the original matrix. That's going to be true if and only if B equals C. A does not have to equal D. This is A here. This is A transpose. They're equal if and only if, yes, C equals B and B equals C. That doesn't always happen, of course. Usually that doesn't happen. But when it does, that seems like it's special enough to maybe have a name. Actually, it's not clear why it's special, but it is. It is special enough to have a name called a symmetric matrix, and it doesn't matter what A and D are. They can be anything. I happen to pick A and D to be the same for this example. I'm going back to the original. But I didn't have to. It just makes the math work out nicer when I do. The eigenvalues of any symmetric matrix with real number entries are always going to be real numbers. That's a mathematical fact that you can take to the bank and you should know for exam 4. The eigenvalues of any symmetric matrix, 2 by 2, 3 by 3, 4 by 4, it doesn't matter the size, with real number entries, as is our usual case, are always real numbers. And in this case, they turn out simple, 5 and -1 for this example. You could quickly figure that out if I asked you right, you've done that many times now. Quickest way is to see the trace is 4 and the determinant is -5. The characteristic polynomial would be A is our example here, 2, 3, 3, 2. Characteristic polynomial is lambda squared minus the trace times lambda plus the determinant. And this factors as lambda minus 5 times lambda plus 1. And the eigenvalues, yes, are -1 and 5. What about the eigenvectors? In this case, they're 1, 1, or any non-zero multiple of that, and -1, 1, or any non-zero multiple of that. And notice there's a relationship, a special relationship between these two vectors, 1, 1 and -1, 1. What do you think, you know what relationship I'm hinting at here? Those two vectors are related in a very special way. They're orthogonal. Their dot product is 0, right? Dot product of those two vectors would be -1 plus 1, 0. They're orthogonal. They're perpendicular to each other. That's another fact you can take to the bank about symmetric matrices with real eigenvalues, with real entries, is not only do they have real eigenvalues, their corresponding eigenvectors are orthogonal to each other. And it turns out that when you normalize those orthogonal vectors, the word normal has different meanings with vectors. One meaning is perpendicular. That's not my meaning here when I say normalize. The meaning I'm talking about is find unit vectors in the same directions as those vectors by dividing them by their length. This vector, in fact, both vectors have length square root of 2, right? Square root of 1 squared plus 1 squared. If I multiply that vector by 1 over the square root of 2, I'll get a unit vector. Make that unit vector be the columns, the first column of P, the change of coordinates matrix. Which sounds like it could be nasty. I mean, really? Square root of 2 in here? But it actually makes things simpler, believe it or not. I'll do it with the second column as well. So far what we're doing here is our standard stuff to do, not from the differential equations textbook, but the linear algebra parts of the lectures that apply to differential equations. We're trying to diagonalize A, evidently, right? We're trying to find a change of coordinates matrix P that will diagonalize A. A is diagonalizable because it's got distinct real eigenvalues. This matrix should do it. If I do the inverse of P times A times P, that should be diagonal with what should be in the main diagonal. What two numbers? You're looking at them somewhere in this picture here. The eigenvalues 5 and -1, except they don't look like it at first. Okay, do simplify inside here. There it is. They didn't look like 5 and -1, but they actually were. That was guaranteed to happen by everything we've done so far. When you, and this is not a unique P. I could have done the simpler looking P, 1, -1, 1, 1. That would still work. So why do the more complicated P? Because even though it looks more complicated, if you had to do these calculations by hand, it's actually easier. A little bit at least, when you know what you're doing. Because the inverse of P in this example is its transpose. Huh? Is that right? By taking those vectors here, normalizing them, dividing them by their lengths to get unit vectors for the columns of P, I have made a matrix whose inverse is its transpose. This matrix, look at it, is the transpose of this one. The first row of P becomes the first column of P inverse. And the second row of P becomes the second column of P inverse. Why is that a good thing? Because it's really easy to figure out transposes, that's why. And this process works even with bigger matrices. 3 by 3, 4 by 4, 5 by 5. It doesn't matter the size as long as it's square. It could be 100 by 100. This process of taking your eigenvectors, which will all be orthogonal when A is symmetric, normalizing them, putting them in the columns of P, will always be guaranteed by some theorems that can be proved to create a matrix whose inverse is its transpose. And therefore, even if it's a 100 by 100 matrix, it's easy in theory to find the inverse. Though in practice, it would take a long, long time to write it down. Right? And probably you'd want your sheet of paper to be huge. Anytime, in fact, a matrix has columns that are both orthogonal and unit length, its inverse will be its transpose. So such matrices are special. Symmetric matrices are special, and such P matrices, which are not symmetric, by the way, because the transpose of P does not equal P, but it's still special. It equals the inverse of P. Such a matrix is called an orthogonal matrix, which is unfortunate. because it would be better to call it an orthonormal matrix. Not just orthogonal, but all the vectors normalized. These two columns do form what's called an orthonormal basis of R2. When you put them in a matrix, we call it an orthogonal matrix. It would be better to call it an orthonormal matrix to be consistent. But again, the big point here, the big picture point is when P is orthogonal, when its columns are orthogonal to each other and unit length, its inverse will be its transpose. And that's a great thing because it makes calculations a lot simpler, especially when you get bigger than 2 by 2 case. Finding the inverse of a 100 by 100 matrix, a general 100 by 100 matrix would be really, really hard even for any kind of computer program. Take a really long time. Now, sometimes there are specialized techniques that apply in special cases that can help you find inverses of a 100 by 100 matrix, not too terribly, but in general, it'd be a really hard thing. I wouldn't want to even attempt that in Mathematica. I'm sure I'd probably crash the computer. That's how difficult it is to find the inverse of a large matrix. That's how many computations have to go on. The number of computations that has to go on in the general case probably is bigger than the number of atoms in the universe. Okay, it's probably like for 100 by 100 matrix, it's probably on the order of 100 factorial. So it's just computationally nasty. So it'd be great if whenever we can do this. And we can do this when the matrix, original matrix, is symmetric. Let's jump to the other punchline we've been talking about. How do you use this information to like solve the system? Again, in our DiffEq book, we solve the system without doing diagonalization. We write down our linearly independent eigenvectors and form our general solution using E as well. And then use that to solve initial value problems. But it is also related to diagonalization, which is related to change of coordinates, skewed coordinates. That's what, see, the linear algebra gets at what we're really doing deep down. It's getting at really why the methods in the book work deep down. That's why it's worth doing the linear algebra stuff. Let's write some stuff down, and then we'll have Mathematica do the calculations. Okay, and all this stuff is fundamental. We're in the core of the course right now, right? This stuff, the last couple of weeks and now, this is the core or the heart of the course. Okay, this is the key stuff to get to come out of the class with. And so you want to make these connections by thinking about it as you work through exercises, examples, including in the lectures and the PowerPoints, to really try to get this. What are we after again? So we're in this case. We're after trying to use linear algebra essentially in ways other than the textbook does to solve this system. And also, for sake of completeness, let's make an initial value problem. Also, for sake of completeness, solve the analogous difference equation, which I can just write as one equation, and it's implicit that there's an initial condition. And I guess I've been using X for the vectors over here. And usually been making them lowercase. Xn equals a, xn minus 1. For n equals 1, 2, 3, etc. This does implicitly assume there's an initial condition vector x0. Back over here, what is the beautiful generalization? It's this. It's the unique solution of this. What is the formula involving the matrix exponential? That's what I'm calling the beautiful generalization. If I want to use my capital phi notation, that's my function. My function name, I use a capital letter to emphasize it's dealing with vectors instead of scalars. Lowercase phi goes with scalar equations. That's just my convention. The subscript emphasizes the initial condition. Think of that as fixed. T is the variable. We're not thinking about flows at the moment. The formula is e to the TA times y0. The fact that that is the solution is the beautiful generalization. Then the question is how to compute this. Well, y0 is whatever it is. How do you compute the matrix exponential e to the TA? You use diagonalization when A is diagonalizable. You replace A with P, D, P inverse, assuming A is diagonalizable. That can be done. If it's not diagonalizable, if there is no such diagonal matrix D, maybe we can do something else. That comes up in lecture 27C. The Jordan canonical form stuff that I mentioned last Friday is what comes up when A is not diagonalizable. I'm not going to talk about that in class here, so it's something to watch in the lecture. Yes, another C lecture this time. But this still begs the question, how do you do this? It turns out you can prove, using the definition of the matrix exponential as a Taylor series, that this is the same as P times e to the TD times P inverse. In other words, we only need to exponentiate D and then use the change of coordinates matrix this way to get back to exponentiating A. And e to the TD is supposed to be easy because when D is diagonal. E to the TD will also be diagonal. Zero's off the main diagonal. And on the main diagonal, you'll have e to the lambda 1t in the first spot, e to the lambda 2t in the second spot, e to the lambda 3t in the third spot, etc. So this is doable when D can be found, when a diagonal matrix can be found, when A is diagonalizable. Again, when A is not diagonalizable, you can still do this stuff, but D would not be a diagonal matrix. It'd be some other non-diagonal. Turns out it can be upper triangular. And that's like the second best we can do. This does have to be e to the TA. I think we won't have time for Mathematica, so I want to try to wrap this up in a couple minutes here so give you some time to work. In the difference equation case, I don't use the phi notation. I can write the solution x sub n as a to the nth power times x0. That's the beautiful generalization in discrete form with difference equations. But raising a matrix to a power is difficult in general, unless you diagonalize, because diagonal matrices are easy to raise to powers. Oops. Oh, sorry. D to the n. Sorry. I wanted to show two steps, sorry. The first step is to say a to the n is p d p inverse to the n. But then, made a mistake there again. But then it can be proved that that's the same as p times d to the n times p inverse. So with differential equations, you do matrix exponentials. With difference equations, you do matrix powers. And when D is diagonal, E to the TD is easy to compute, and also D to the N is easy to compute. That's the big picture of how to relate the linear algebra to the differential equations. And we can do more. We can relate it to skewed coordinates and that kind of thing. And the change of coordinates like we talked about last Friday with a new variable like U. By the way, when you change coordinates to U to get a simpler system, like an uncoupled system, it's analogous to doing U substitution for integrals. You're just trying to make the problems look simpler so you can solve it more easily. That's what we're doing when we change variables to skewed coordinates, where the new axes are on the straight line solutions parallel to the eigenvectors, is we're making the system look simpler, easier to solve. But we got to translate back to the original system by doing the PDP inverse stuff. That's how you translate back to the original. Okay, you've got 20 minutes to work. You want to ask any questions? Anybody? You feel free to ask questions about what I'm talking about here.